This is Physics 1C for May 13th. Sorry, go ahead. So look, we're looking at the circuit right here, and the question is, if we look at the circuit right here, the question is, what's going to happen to the bottom light bulb when I open the switch? So go ahead.
I mean, okay, so it's still connected to the top circuit, which has the inductor. So when it opens, the inductor is going to try to keep the current going.
Mm-hmm.
So
what direction do you think the current in this bottom segment here is going to go whenever I open this switch?
it's going to go the opposite direction.
Why is that? You're saying basically all these electrons here are going to start flowing the other way. Why is that?
And that's because, well, the inductor is going to try to keep the electrons flowing in this, towards the, oh my God, what is it? The left. So the other electron, to keep the current going, the electrons are going to have to start moving to the right.
Okay, and why does the inductor do that? What's the reason for that? You're right. This inductor is going to want to keep these charges to flow the way that they're going right now. Now, it can't do that forever, but it can do it for a short amount of time. What's the reason why?
This inductor is going to smooth out changes, right, in like the current.
Yeah.
I would say like Lenz's law.
Sure. Yeah, so the inductor, the way I think about it is, the inductor can act just like a battery, basically. It can be a source of charge. It can be a source of EMF, basically, right? And when you're turning the circuit on, it acts as a source of EMF opposite to the direction the current wants to flow, because it's always going to oppose changes. So when you turn the circuit on, here, we'll do this. You can see that you were right, by the way. I don't know if you all noticed. We'll look at it in a second. When you turn the circuit on, you're going from zero current to something, which means that the inductor is going to say, well, you can't just instantly do that. So it's going to set up a reverse EMF, okay? And you can't see it on here. The only way you can see it is just that these electrons in the top here are flowing a little more slowly. Okay. Now, when we open the circuit, it's reached maximum, right? Almost reached maximum. When we open the circuit, now what the inductor is going to do is, instead of making the current want to flow back the opposite way, it's going to want to make the current keep going. Because again, the inductor acts like inertia. So if the current's already flowing to the left, the inductor is going to help it to keep flowing that direction. But not forever. It's eventually going to run out. Just like a capacitor, eventually it's not going to have any charge. It's not going to have a magnetic field. So, yeah. What'll happen is that it's going to keep pushing the charges this way, and we can see that. You can watch on this graph right here if you want to. Let's go down to like this scale. And we should see the current basically kind of decay down to zero. Okay, let's see if that happens. But you can also watch the electrons in here, because you'll see them change direction the moment that I lift this open. You see that? Now, the inductor can't power the light bulbs for very long, because its energy comes from its magnetic field. You can't see it on here, but when there's current flowing through this inductor, there's a giant magnetic field flowing through it, right? And the current is actually flowing the opposite direction as these little balls. The current's actually flowing that way, which means there's a magnetic field inside of the inductor that points this way. And when you turn the circuit off, that magnetic field takes time to decay. It doesn't just decay away instantly. It takes time to decay. And when it's decaying, it delivers power to the circuit, just like that. Of course, it eventually runs out of energy, right? So this is a pretty good circuit to kind of show what's going on. And we can slow and speed up the rate at which this process happens. Like, for example, if we wanted to, let's let it decharge. Let's put a bigger inductor in here just to kind of like go through what we talked about last time. What happens to the rate at which this occurs if I make this 100 henries? Is the light bulb going to light up faster now that it's bigger, or is it going to light up slower now that it's bigger?
Lower.
Yeah, slower. So let's watch. Yeah, you can see that these electrons are having a really hard time pushing through here, right? I mean, it's almost like you can almost tell that it's like they're heavier. Like these electrons are heavier than the ones down here. They're not really heavier. They're all just electrons. But the difference is that a lot of these electrons are putting their energy into creating a magnetic field inside of this inductor. Okay. Once the magnetic field has reached its maximum value, which is going to be, we've got a voltage, right? And our upper circuit has a resistance. So at some point, you're going to have, 25.88 divided by 10. Flowing through this top circuit right here, you're going to have 2.6 amps, right? It doesn't say 2.6 amps here, but it should, right? Am I wrong about that? Why is it only reading 1 amp? Does this thing have, and it doesn't have a... Am I crazy about that? Shouldn't the current be like 2.5 amps? Let's see what would the current in this section be? Shouldn't it be 25.8 divided by 20? That would be what? 1.25? Yeah, maybe this current chart isn't exactly accurate. I wonder if... Uh-oh, I think I broke it. I wonder if we actually use this one. Here, will this unbreak it if I do this? Uh-oh. Yeah, that's the one thing that's really bad about this. You do one thing and then it gets mad at you. And there's like really no way to... Okay, I wonder if I save it. It's too bad. Let me do that. Okay, well, I've mostly said... Go ahead.
Would current keep flowing if these were like superconducting currents? If there's no resistance?
Yeah. Yeah.
When you open it, when you open the switch?
Yeah. As long as the inductor was made of a superconducting material in the wires and the resistor. If everything was made of superconductors, then yeah, there'd be nothing to stop it from flowing, right? The only reason this current stops flowing is because... here, I don't even know if this is going to work, but I can show you a circuit where the current will flow forever if you want, like you're talking about. At least I think it will. I don't know what's going to happen. We'll find out. So what will we need to do? We basically just need to have a circuit where the only resistance is in the bottom. I think what's going to happen probably is that the whole circuit's going to catch on fire, but we'll see what happens. But yeah, I mean, superconductor means there's no loss of energy, basically, right? So when you have current flowing through a wire, it has energy, right? It has basically kinetic energy, right? We call it electrical energy, and we define it in terms of like the rate at which the energy is being consumed or whatever. But okay, so this should do. I think this should work. I'm pretty sure if I close this, that we're going to get current flowing through the system, and then when I open it, there should be a current flowing in just the upper segment that should flow forever. Let's see what happens. I think it's just going to catch on fire though. It doesn't like it when you don't put resistors. By the way, this is true of real circuits, too. If you connect a circuit up and you have no resistance in your circuit, then what's going to happen is that the current's going to flow at a really high rate, and it will usually burn the circuit, if that makes any sense. It's too bad we can't do labs, because you guys would have burned up a bunch of circuits by now, and you learn something from it, right? You learn, oh, okay, I can't connect things like this. And you'd do things like you'd connect something and you'd see a massive spark come out, and you'd be scared, because obviously you hear a loud pop and a spark, you should be scared, right? Yeah, it's too bad we can't do all that stuff, because honestly, that's really kind of the fun part of this class, in my opinion, is doing those labs. And we do have really good labs for Physics 1C, in my opinion, but anyway, we get this. Yeah, look, it's not gonna fix itself now. Now, if I were to do this, I wonder if I could put a resistor in and then just drop the value to 0. You can make it 0. Okay, so what if we just make it really small? It should allow the current to flow for a really long time. I'm not going to be able to get this to work anymore. It's just not going to work anymore. Everything's connected. It's just, as soon as you crash it once, it's like the whole app just stops working. I don't really know why. Okay, so we want to keep talking about inductors, and these are the topics that I'm going to try to cover. We're not going to get through, we might get up to here, but I doubt it. I think we're just going to cover the first 3, and then we'll cover these last 3 next time. So now that we know what an inductor is, the next thing to talk about is the EMF of an inductor. So let's do that. Okay, so let's start with the circuit. We have some battery that has some EMF, and we're going to connect it up to I guess we could put a resistor in here. There's nothing wrong with that. And then we'll put an inductor in here. So just to remind you, this is what a resistor looks like. Jagged lines like this, like zigzags. And an inductor, which we use the symbol L for, looks like this. And again, an inductor is literally just a coil of wire. So let's say that we have current in this circuit and it's flowing. Let's go full screen. And let's put a switch in here so that we can say that we're going to close the switch at t equal to 0, because the thing about inductors, okay, is they don't do anything unless the current changes, okay? I guess I could write that down, but I don't think I need to write it down. The inductor only responds to changes in current, right? What does a resistor respond to? To compare, what does a resistor do in a circuit? What does it respond to? Does that question make any sense?
I'm trying to think. Inductors change the change in current, and then the resistor just kind of like responds like to the current or something.
Yeah, just to any current at all, right? The resistor will, I guess what the way to ask this question is, when does a resistor do something in a circuit? And it does something as long as there's current flowing, right? It does nothing when the current is 0, right? What the resistor does is it basically obeys Ohm's law, right? Delta V across the resistor is equal to I times R, right? So if the current is 0, the resistor isn't doing anything. And what the resistor really does is it basically, well, can anyone tell me, what does a resistor do? Fundamentally, what does a resistor do?
Resist current?
It resists current, and how does it, like what is, when it does that, what effect does that have? How do we use them? Like, what are the purpose of them?
It just slows it down.
Okay, it slows current down, that's true. What else does it do?
It it kind of dissipates it. It could dissipate it in the form of heat.
Yeah, that's the main thing it does. A resistor, I'll put both the things you all said down, slows down the current and transforms the energy of electricity into heat. It's probably the simplest way to say it, just to use language that everybody would understand. In terms of physics, we would say it takes electrical energy in the form of flowing electrons, and those electrons collide with material that the conductor is made out of, and when that happens, the material itself starts to vibrate more frequently, which means the temperature of the material increases. And if you try to pass too much current through a resistor, it will burn. Okay, so that's what a resistor does. It slows current and transforms electricity into heat, okay? What an inductor does, an inductor, it only responds to changes in current. So the resistor does something as long as you have current. As long as you have some kind of current, the resistor is going to do something. The inductor is only going to do something when you change the current. So once the current reaches its maximum value, the inductor is not really doing anything. Once the current drops to 0, the conductor is not really doing anything. The inductor. But as long as the current is changing, the inductor is going to do something. And it has the effect of when you try to increase it, the inductor sends back EMF, and when you try to reduce it, it sends kind of forward EMF, basically, right? Okay, so that's what it does. It responds to changes in current, has the effect of kind of damping them out and making the changes smooth as opposed to sharp, okay? Now, if we want to define how that happens, what we can do is we can say that when you have current in a circuit that's changing, okay? So if we throw this switch at t equal to 0, that's going to lead to di dt, the rate of change of current in the system, is going to be greater than 0. Okay, and let's use, I don't know if it matters if we put I or a capital I, but let's use a little I right here. So we close the switch at t equal to 0. So the switch is closed, and that means there's going to be a current flowing through our circuit that we call little I. And I'm going to say that because we close the switch, the di dt is going to be positive. So the current is growing over time, okay? What's going to happen in the inductor is the inductor is going to set up what we call a back EMF, okay? And in this particular case, that back EMF is going to go this way. I'm going to call this E sub L, and I'm going to say this is the back EMF from the inductor. Okay, it's going to go back to the left. We can write an equation for it. The EMF of the inductor is going to be equal to negative L, which is the inductance, multiplied by the derivative of the current, or the time rate of change of the current. Okay. So this quantity, EL, is greater than 0 when... So L is always a positive quantity, okay? You cannot have an inductance L. Remember, L is measured in henries. Just like resistance, there's no negative resistance, there's no negative inductance, okay? So this quantity, E sub L, is positive when what is true? When is this positive?
When the rate of change of current goes down.
Yeah, when dIdt is negative, right? So that is to say when the current is decreasing, right? And the EMF of the inductor is less than 0, which means this is like back EMF, basically. When the rate of change of current is greater than 0. That is to say that the current is trying to increase. Okay, does that expression make sense to you? You take the inductance and you multiply by the time rate of change of the current.
Yes.
Now, I can write this in another way so you can understand where this comes from. This is really just Faraday's law, if you think about it, because L, I said last time, was equal to negative N times phi B, the flux through the inductor, divided by the current flowing. Sorry, there's no negative sign here. I don't know why I put that on there. So if you plug this into this equation, what you get is EL is equal to negative L times, whoops, my bad. This is going to be kind of weird. How does this end up working out? So if I plug in L into this equation, we're going to have an N, a phi B, an I, and a dIdt right here, right? So how do we turn this into Faraday's law? The first thing I could say is like, well, what if we just pull all of these things, the flux and the current, into this equation right here? If we do that, then we'll reproduce Faraday's law, right? But that doesn't seem right? I can't just take phi and I and just shove them into this equation, right? So I think you'd have to start from Faraday's law, basically, to get there, I think. And you'd have to factor out the things that become constant or something like that. Yeah, I've never actually tried to derive this before. I just kind of was noticing that we had learned this last time in this one, and you look at them, it kind of looks like Faraday's law, EL equal negative L dIdt. But if we start with Faraday's law, I wonder if we can produce that equation. So how do we get from here to here? We'd have to plug in that the flux is equal to this, basically, right? So the flux would be, what is it? I, L,
over N.
Over N, right? Yeah.
Let's see.
That should work, right? Because now it'll be negative N d of I, L over N. Yeah, this is going to work. dt. And then you just say N and N cancel. L is a constant, so you put it in front. So there we go. Yeah. This works. Okay, so that's how you derive it. I guess I could just do that in the future. We could just derive it that way next time that I teach this, I guess. So yeah. So this is really all the EMF of inductor is saying is just Faraday's law, basically. Has the same negative sign, and the EMF is, again, positive when dIdt is decreasing. When the current's going down, it's positive. That means that, so I drew one of the scenarios. Let's draw the other scenario. So the scenario when the current is increasing is you close the switch, there's a current that flows in the circuit, but there's also a back EMF that goes backwards. And that's happening because d I dt is greater than 0. The other possibility would be I have a circuit where I have a switch and then I also need an upper segment of my circuit. So we'll draw another resistor in here. So the other way we could do this is you could say, suppose that I have a switch that's been closed for a long time and we open it. So the switch starts off closed, and then we open the switch after it's been closed for a long period of time. So if the switch has been closed for a long period of time, there's going to be a current flowing through our circuit right here. We'll call it I. It's going to flow this way. We'll call it I1 up here, and it's going to flow this way. We'll call it I2 in this segment here. So what happens is if you open the switch, then there's only going to be current flowing around the top right here. And what's going to happen is that when you open the switch, you're going to get an EMF in your inductor that's going to go in the same direction. Because if you open the switch, that means that di dt is less than 0. So what's going to happen is that the inductor is basically going to keep the current flowing this way. Okay, so after you open the switch, what's going to happen is that you're no longer going to have current down here. You're no longer going to have current flowing this way. It's going to switch direction because the inductor is going to act as a source. And it's going to make the current flow around like this. And we saw this in the thing that we started class with today, that circuit. Okay, does anyone have any questions about the EMF of an inductor? Should we do a calculation to see how big this might be?
Sure.
Okay, so let's see if we can concoct an example. All right, so we're gonna make a circuit, and we'll just keep it simple. All right, we put two things in here. One's going to be a resistor. One's going to be an inductor. We're specifically going to look at RL circuits here in a second, but for now, let's just look at the inductance part of this. Okay, we put battery in here. So we'll do 10 volts. And switch right here. We'll say it closes at t equal to 0. All right. So we need to pick a time interval over which the current is going to reach maximum. And to do that, I'm going to put some numbers in here. Let's say this is 100 ohms. And let's say the inductor is like 0.5 henries. Okay. Okay, and then let's say that when we close the switch, .5 divided by 100 is equal to what? 0.005, right?
Yeah.
Okay, so let's say that the current, I'm just going to go this way, reaches, or I'll say it like this. We'll say that current goes from I equal to 0 amps to I equal to, the maximum current in this case would be 10 over 100, right? So 10 divided by 100 is 0.1. So 0.1 amps in delta t is equal to 0.025 seconds. Okay? What we want to do is to find the, I guess, average back EMF. I think that's a reasonable thing to calculate. Okay, so to do this, and I'm pretty sure you're going to have problems that show up like this on your homework too, what we're going to use is that the EMF of the inductor is going to be equal to negative L, and we're just going to use delta I over delta T here. This is how this would be taught in like Physics 2B, but I often find that when something is taught, like, and I give you an equation that has some calculus in it, like this one, that people forget that this D can also be a delta. So, all right. So we'll use this. And yeah, we have all the information we need. So this is going to be equal to negative L, which is 0.5 Henry, times delta I over delta T. So that's going to be 0.1 amps minus 0 amps divided by 0.025 seconds. And we're going to get our back EMF then. It's going to be equal to. So the negative sign here just tells you what direction it points. .1 minus 0 divided by 0.025 times.
I got 2.
2.
2. Yeah, I don't know how reasonable these numbers are. It seems kind of high, doesn't it? But that's the average, so I don't know. Kind of weird that this number ends up being bigger than this number, but I probably just did something wrong when I picked all these numbers here. I was trying to come up with something reasonable. It shouldn't be
2 volts.
Oh, it's volts. This actually does work then. Okay, that makes way more sense. I'm an idiot. Yep. I'm glad you pointed out. It's 2 volts. So then we could use this to find, like, the back current if we wanted to, right? For that, we would have to take the EMF and divide by what?
Resistance.
The resistance of the circuit, right? Which in this case is 100 ohms. So what we would get is negative 2 volts divided by 100. So this would be 0.02, right?
Yeah.
Amps. Okay, there we go. That number makes sense, actually. So this would be the back current. So what happens here then, we can draw it on the picture here. There's a back EMF going this way. That's EL. And you could also say, in a way, that means that there's a current that's flowing back this way that we call I back, if you want to, or something like that. Okay. All right, does that make sense? You have any questions? So we can compare some things here. You notice that the EMF is 10 volts, but the back EMF is only 2 volts. So that means that if you think about this, the average EMF that's being delivered over this period of time from the battery is only 8 volts. Does that make sense?
Yeah.
10 minus 2. And that's because this battery doesn't get to do its full job until this inductor is completely powered up. Once the inductor once you get to maximum current in the circuit, the back EMF goes away. Does that make sense?
Yeah.
This is an average over this entire time interval. And this might not seem like a long time interval, but in the case of this circuit, this is about the time it's going to take for the circuit to reach its maximum current. Okay? So after it reaches maximum current, the inductor literally isn't going to do anything. It's going to have this big magnetic field that it's holding. It has some energy in that field, but that's about it. Okay, so, yeah. Any questions at all? Does this make sense? Okay, the next thing we want to do is to look at the energy of an inductor. This is very, very easy to do. So we take a circuit and we look at an inductor inside of that circuit. So here we go. We have an inductor, L. It is connected to, do we want a resistor in the circuit too? I think we want to just do pure inductor for what we're going to do here. Okay. With inductors, we always have to put switches in here because the inductor isn't going to do anything unless there's a time interval over which it charges up. Does this remind you of capacitors? You know, when we were talking about capacitors in the past, the circuits that we looked at, you know, we talked about what happens when you close a switch and there's a capacitor in a circuit. It takes some time for it to charge up, right? And then once the capacitor is fully charged, basically no current flows in the circuit anymore, right? So we were always looking at what happens when you turn the circuit on or off with a capacitor for the process of how it gets charged up. And then we also talked about what happens when it's fully charged, right? So it's similar with inductors. You have to have some kind of a switch because all we care about is what happens when the current changes. Now, this is all going to change in the next chapter because we're going to stop talking about only DC circuits. And what we're going to find is that inductors and capacitors both become much more interesting when we talk about alternating current circuits. When the current flows left and right, back and forth, the inductor is going to be able to do what it does, which is resist changes in current constantly. And the capacitor is going to be able to do what it does, which we'll learn about, which is it's going to be able to charge, discharge, discharge constantly. So the fact that it creates a short circuit doesn't really mean anything at that point. Okay, we close the switch at t equal to 0. That causes a current flowing through the circuit to be I. And what we're going to look at is the power delivered by the inductor, I think. That's what we're going to look at. Okay. And for that, we're going to use our old definition of power for electricity, which is power is equal to current times the EMF. When we turn this circuit on, what's going to happen is there's going to be a back EMF across our inductor, EL, that goes this way. And we know what that's equal to. We know that EL, as we just said, was equal to negative L di dt. Right? So now what we're going to do is we are going to, what's the best way to do this? One way to do it would be to say, we can say that power is the rate at which energy is delivered. So we could say that it's the time rate of change of mechanical, or not just mechanical, of energy in the system. Just to be really clear, I'm going to say derivative of energy with respect to time. When I write power and then I write d energy dt, do you all agree that these are the same thing?
Yeah.
Yep.
Okay. And then on the right-hand side, we have negative IL di dt. So now what we can do is, if we want to, we can basically get rid of the dt's. So what we have on the left-hand side is, I'm just going to put dE. And what we have on the right-hand side is negative IL di. And what we're going to do next is we're going to integrate. We're going to integrate from 0 up to the maximum current that's going to flow through our system, which I'm just going to call I. And then on the left side, this is just going to give us the total amount of energy, E, that's stored inside of our inductor. I'm going to call it, I think the book usually likes to use U's for these, actually. Let's do that. Let's use what the book uses so you don't get confused when you go back and look at it. We're going to use U for energy. So we'll use U here. Sorry about that. Okay, and then I'm going to say this is U sub L, the energy of the inductor, is going to be the integral of this. So if we integrate this, I think what we're going to get is negative 1/2 L times I squared, right?
Mm-hmm.
Okay, and I now realize, as I'm going through this, that this negative sign is kind of meaningless when we talk about power, right? So it just really isn't important. So what I'm going to do is I'm going to drop absolute value sign on here so we can get rid of the negative sign. So we'll just make this plus, 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 and then I'm just going to get rid of it down here in the last line because that's what we want for our answer. And I'll just say again why I did that. When we talk about power, you know, when you go buy a light bulb, the light bulb says 60 watts, right? You've never bought a light bulb that says negative 60 watts, right? So even though power can be negative, you can have something that's sapping power from a system. It's not going to be useful to us in this case. So this is the energy stored inside of an inductor right here. 1/2 Li squared. You have any questions about that? Okay. I want to take a moment to compare this inductor stuff to mechanics. When I say mechanics, I mean physics 1A, basically.
Wait, quick question.
Yeah.
In the integral, is that capital I just like the maximum current that you could reach?
Yeah. I is going to be equal to max current. Yep.
All right, thanks.
No problem. Okay, so we want to relate these topics to mechanics. Okay, so what are the two things that we just learned about? We learned about the EMF of inductor, which is ended up being equal to negative L di dt. And we learned about the energy stored in an inductor, which is 1/2 Li squared, right? So in mechanics, there are equations that actually have direct analogs to these two, okay? And what they are is, well, let me see if you all can figure this out. What does current correspond to if we go from electricity back to mechanics? What does current represent in mechanics?
Velocity.
Velocity, right. So this is like v squared, right? What did I tell you inductance was related to?
Mass. The inertia.
Mass or inertia. So then if you basically do kind of an analog like that, this equation becomes 1/2 mv squared, which you will all recognize is, what is this?
Kinetic energy.
This is kinetic energy, right? So let's think about this. What this is saying is that you can store energy inside of an inductor, and the amount of energy you store is a 1/2. We don't care about this. It's basically related to how big the inductor is. That is to say, and remember what the inductor is, just to remind you, for a solenoid, that this equation becomes, I think it was mu naught capital N squared divided by the length of the solenoid times the cross-sectional area, right? So a solenoid that has some current flowing through it has energy that's related to this quantity. This quantity basically tells you how many coils you have, how fat it is, and how long it is, okay? The shorter it is, the better. The wider it is, the better, and the more coils, the better. But all of those just end up giving you a number that tells you how well your solenoid can have currents induced inside of it, basically, right? So that gives you a number, and again, that number means that it's going to have the effect of causing the electrons in the circuit to act sluggish, to make them move more slowly, and not more slowly, but to make them harder to speed up and harder to slow down. So again, you get that. And then it says you multiply this by the rate at which the electrons move, because that's what I is, right? So this quantity tells you effectively how massive your electrons are, and then the current tells you how fast they're moving. When you combine those two things together, you get a type of energy, and we call it the energy of the inductor. But it is a type of kinetic energy, right? It's kinetic energy it's energy that's only there because the electrons are moving. If the electrons stop moving, you have no energy in the inductor anymore, right? That is to say, if I just take a coil of wire and I don't hook it up to anything at all, it's just a random coil of wire, that wire has no electrical energy, right? If I just take some random coil of wire, you have no energy there, right? But the moment that you start to flow current through it, all of a sudden, now you have energy. We say, oh, there's energy stored here. In fact, what we can do is we can say that this is the energy of the electrons, if you want to, or what you could say, it's the energy of the magnetic field. That's usually what we say. It's the energy stored in the magnetic field of the inductor. But I prefer to think about it as the energy of the electrons. They have this energy because they're already flowing in a certain direction, right? They want to keep flowing in that same direction. Just like go out to any highway in California and you're going to see tons of cars flowing along the road at 60 to 70 miles an hour or something like that, right? All those cars flowing together are like a bunch of electrons that are flowing together. And just like you couldn't just stop all those cars from moving easily without creating like noticeable changes, you can't stop the electrons from moving instantly either, right? They want to keep flowing as long as there's a path for them to flow along. They won't flow if there's no path though, right? But when they're flowing, they carry a bunch of energy and it's hard to slow them down and it's hard to speed them up. In fact, if you really think about the way that like I squared works, right? You might get an understanding of why this is so hard. When you want to increase the current by a factor of 2, how much are you increasing the energy stored in the inductor? So if you want to go from like 1 amp to 2 amps, how much does the energy of the inductor go up?
By 4.
By 4, right? So that means you need to put in 4 times as much energy into your circuit to get all those charges to move faster, right? Does that make sense? If there was 1 joule of energy in there, you're going to have to add 3 joules to the system just to get the charges flowing, right? And once they're already flowing, you're going to need to extract energy from the circuit to get them to stop, right? They won't just stop on their own. They want to keep going because they have, in a real way, they have kinetic energy. They have inertia and they have a speed, yeah? Okay. So that's what that equation is. Now, this one's a little trickier. Okay, does anyone have any question about that? The connection between the energy of the inductor and kinetic energy? What do you all think the left equation represents?
That looks like force.
This is like force, yeah. So the word EMF stands for what? What does EMF stand for?
Electric motive force?
Yeah, electromotive force. The F stands for force. And this is because when people were first learning about circuits and they learned about what voltage was, this is the old-timey word for voltage. Nowadays, we just use the word voltage or potential difference, right? But this is the old-timey word because they thought it was a force. They thought voltage was a force. It's actually energy, right? But they thought it was a force because it had the effect of pushing things, right? And when you look at this equation, it's basically like saying that force, because this is like our force, is equal to mass times the rate of change of velocity. Or roll the mass inside of here so that it's this. And it becomes the rate of change of the momentum. Or, another way to do it, what's dv dt? What's the time rate of change of velocity?
Acceleration.
Acceleration. So you can either say that this is F equals ma, or you can say it's F equals dp dt. Doesn't matter. Doesn't matter. So, and I mean, think about it. That's what di dt is, right? It's acceleration. When you try to change the current in a circuit, you're accelerating the electrons, right? If you try to shut the circuit down, you're trying to take all these electrons that were moving in one direction and make them stop, right? You're trying to make them stop moving. And that requires time, number one. They won't stop moving immediately. And it requires energy as well. So, one way to talk about that is saying force is equal to mass times acceleration. The charges are already moving in one direction. It's going to take a force to stop them from moving, and that's going to cause them to decelerate. Or you can think about it as you've got all these electrons moving. They carry energy, and that energy can't just disappear. It has to go somewhere. So however you want to think about it. For me, this makes understanding what inductors do a lot simpler. But I'm already very comfortable with physics, so it's natural for me to want to use a physics-to-physics analogy, but I do understand that this isn't a great way to understand things if you're not super comfortable with physics. But I think if you're in 1C, I think it's pretty safe to say you're pretty comfortable with the concept of kinetic energy, right? It's one of the things that we kind of like ram down your throat in Physics 1A, so... Right, you all are pretty comfortable with this idea? Am I wrong about that? You all said kinetic energy the first thing when I wrote it down, so I kind of assume so. All right. Any questions? Okay. Just one second. I had a problem that I wanted to do, and I have to see. I thought that I had copied it, but I don't think I did. Oh, not this one, from this day. Oh, it's an RL circuit, so we're not quite there yet. Okay. Okay, cool. Okay, the next topic is magnetic energy density. By the way, as I'm starting this, how are the homework assignment due dates looking to you all? Like, is there a homework on inductors due this week, or is it like due next week?
Next pass sheet physics is due on Monday, I think.
Do you know what the subject is?
It's an EM inductance.
Okay, so I probably need to push that forward because we're probably not going to cover. Well, I'll probably push that back a week. Unless it's the chapter on Faraday's law, but it sounds like it's not. It sounds like it's on this chapter, right? So remind me after class, and I'll push that date. All right. Magnetic energy density. Okay, so if I have a solenoid, so make a solenoid here. Really bad looking solenoid, but it's not super important. And let's say the current is flowing like this, so it goes up, up that way, down this way, and it comes in right here, I, like this. So this is going to construct a magnetic field that's going to point this way, where we know the magnetic field of a solenoid is mu naught times the number of turns per unit length multiplied by the current flowing through the solenoid. And we also know, as I said above, that if the area of the end cap is A and L is the length of the solenoid, that the inductance of the solenoid is mu naught times n squared divided by the length times the area. And basically, we just want to come up with a way of describing how much energy per unit volume is there in this magnetic field. Okay? That's what we mean by energy density, is energy per unit volume. So the way we're going to do this is to use the definition of inductance, or the energy of an inductor, which is 1/2 times L times I squared. And we're basically going to use these three equations to come up with an expression for the energy per unit volume. So if we put them together, for L, we're going to replace it with this. For I, we're going to replace it with, we're going to solve this for I. So we'll have I is equal to B over mu naught n. Remember that little n is equal to big N over L. So we're going to use that here in a second. Okay. So the current is B over mu naught n. So we put in here B over mu naught times little n squared. And now if we multiply all this out, this whole thing is going to become B squared divided by mu naught squared. And now I'll replace n here. So this is what we're going to replace right here. So it's going to become n squared, which will be n, big N squared divided by L squared. Now we can start canceling stuff. So this mu naught cancels out with one of these. This L cancels out with one of these. The whole n squared cancels out completely. And what we're left with is 1/2 B squared over mu naught times A times L. If I did everything right. Does that look right?
Yeah.
Okay, what's A times L? Area of the end cap is A, L is the length, so what's A times L equal to?
Volume.
The volume.
Yeah, so this is volume. I'll just use the symbol V for that. So what we'll do is we're going to take this, and we're going to divide by the volume, V, and what we'll get is 1/2 B squared over mu naught. And we call this magnetic energy density. Your book uses a lowercase b. I don't really know how to make a lowercase b. Well, the main thing is I don't know how to make uppercase u's that don't look like v's, but that's our magnetic energy density. And we can compare this to electric field energy density, which we derived much earlier on. Does anyone remember what we got when we did this with electricity? There was a 1/2, an epsilon naught.
Epsilon.
What else is missing?
And a E squared.
E squared, yeah. So these two expressions are going to show up again later on, but this is as good a time as any to derive them. So this represents the magnetic energy density. That is the energy per unit volume of the magnetic field. Because if you look at what shows up in this equation here, there is no longer anything to do with the solenoid, right? The solenoid had size A, number of turns in, a length L, and that information is all gone now. And all we're left with is just the magnetic field itself. So what this represents is that if you have a magnetic field in space, there's actually energy associated with it. The field itself has energy. It's energy per unit volume, but it's energy nonetheless. And I think that's kind of fascinating because the magnetic field is such a abstract concept, right? We know it's a vector field, and you can study and understand how vector fields work if you want to. But the reality is a vector field is just every point in space around a magnet has a certain value for the magnetic field, right? And that magnetic field can interact with other magnetic fields. It can interact with iron filings. It can also interact with charged particles if they're moving. So it can do things. But the idea that it contains energy, right, makes it even more... it makes it less abstract. It makes it more tangible. You know what I mean? It makes it more real.
Mm-hmm. I
mean, the reason I'm trying to emphasize this is because if we think about electric fields, right? Remember what an electric field is, okay? I don't know. When you think electric field, I don't know what you see in your brain. I don't know, like... I'm interested. I would very, very interested to know, but when I say electric field, this is all I mean. If I have a positive charged particle, there are going to be electric field vectors, right? That kind of point like this. At every single point in space, you can define an electric field vector. And when you're closer to the charge, those field vectors are bigger. And when you get farther away, they get smaller, right? And all they represent is this... I'm going to use the word imaginary. I don't really mean imaginary, though. This imaginary field around the object that tells you what happens when you come along here and you put another positive charge here. What the electric field tells you is that when I put a positive charge right there, it's going to feel a force, and the force is going to go this way, right? But, just like the question of if a tree falls in the forest and no one's there to hear it, does it make a sound? You all have heard that before, right? If a tree falls in a forest, yeah. What do you think? Does it make a sound?
I mean, it's gotta.
Sure, yeah, I mean...
It should, right?
No one has to hear it.
Just because... Yeah, that's right, exactly. Just because there's no one there to hear it doesn't mean it doesn't make a sound. Of course, if we're all living in a simulation, though, then the answer's no, I think, right?
True.
All right, anyway. Yeah, and I'm only half joking. I think that's true. I think if nobody's looking at something, then nothing's happening. Probably. Anyway, so the electric field's the same way, because you could say, well, what's the point of this electric field vector? Like, what's the point of this? If the electric field vector only does something, right, when a positively charged particle is placed at that location, then what's the point of this vector over here? What if in the history of the universe no charged particle ever comes to this point right here, right? What if there's never a charged particle to feel the force? What's the meaning of this electric field line then, you know?
There's some unused potential.
Some unused potential, that's a good way of putting it. Yeah. It's just like someone that has a lot of basketball talent that never gets to actually play basketball because, whatever, they live in a neighborhood where everybody plays ping pong or something, I don't know. Untapped potential, right? But what these equations tell us, down here at the bottom, is that each, whether it's an electric field or a magnetic field, it doesn't matter which one, both of them store energy. So there's technically, if I were to put a little box right here, I could quantify the amount of energy there is in that box, right? Because I can find out the value of the electric field easily, because we know that the electric field of a point charge is just kq over r squared, right? And I could create a little box right here, and we could do an integral, and we could sum up exactly how much energy we'd have in there. We'd have to integrate because, different cross sections would have, like as you get farther away, like right here, the electric field's weaker than it is right here, for example, right? But nonetheless, you can do an integral, and you can calculate exactly how much energy is contained in that region of space. And I think that's amazing, because it dispels any notion that the electric field isn't real, that it isn't important in some way. If you can quantify how much energy is there, then it's real, right? Because energy is real. You've experienced it in your lives, right? You know that when your car runs out of gas, it no longer has energy to move itself anymore, right? You know that when you haven't eaten food in a long time, you get really tired and it's hard for you to perform physical activities, right? So energy is a real thing. And we also know that there's a connection between energy and mass from Einstein, right? That whether you learned it in this class or whether you've taken 1D or not, like you all know about the connection between energy and mass, right? Which is, how do you all know that energy is connected to mass, or you should know by now?
E equals mc squared.
E equals mc squared, exactly, right? And there's no doubt that mass is real, right? Like when I pick up this remote, it has a mass, and the effect of that is that it has weight because there's a gravitational field here on Earth, right? It would have mass even if there wasn't a gravitational field, though, right? And the gravitational field would be there even if there was no massive object to ever feel it, because there's also energy stored in the gravitational field, right? You learn about it in Physics 1A. There's energy in the magnetic field. It looks like this. That's what the energy of the magnetic field, the gravitational field looks like, right? Mm-hmm. So, anyway, in case you thought that magnetic fields and electric fields were merely just mathematical constructs of physicists, let me dispel that notion and say they contain energy in the same way that your gas tank contains energy, which means they are just as real as the gas in your gas tank. You know what I mean? And that is very relevant to where this class is going, because I have to have you all believe these are real things, or else you won't believe me when I tell you that light is a propagation through these energy fluctuations. Basically, light is basically a fluctuation of energy within these fields, and your eyeballs are really good at detecting fluctuations of the electric field, whether you know it or not. Your eyeballs are really good at that. So, anyway, that's magnetic energy density, and we're going to connect these two things together when we get to the chapter on light. We talk about the energy of a light beam and stuff like that. Okay, go ahead. What's up?
No, that sounds interesting.
So does anyone have any questions or comments? I didn't believe electric fields were real for a really long time. I really didn't. But I believe they're real now.
It's just
That's
something
what I'm
hard
coming
to believe because of you can't really see it.
You can't see
you
it.
can, right? But not in the same way that you can see a car moving or something.
Precisely. That's a really good way of putting it. You can't see them, but you can. Because we can take a magnet, we can drop iron filings around it, and we can see a picture of what the field lines kind of look like, right? The difficulty with observing something is that you need to be able to distinguish it from the process of looking. Like, when I pick up this remote, I know it's a remote because it looks like a remote. I can see it with no problem at all. It has different colors on it, and I can see the 1, 2, 3, 4, 5, and all. Like, I can tell this is a remote by looking at it. You would never be able to see an electric field line, though, because that would be like seeing the way that you see. You know what I mean?
Yeah.
It would be like observing the act of seeing. I'm trying to think of something else that's like that. Yeah, you can't see an electric field for this. I think for the same reason that you can't lift yourself up by your bootstraps, right? There's that expression, like, to lift one up self by one's bootstraps means to, like, overcome adversity and become successful, right? But in physics, it's silly. You can't lift yourself up, right? There's no way to make yourself move. If you were just floating in outer space, same problem. You can't. There's no way to make yourself move, right? We can't move ourselves with our own power, but we can move other things with no problem. We just can't move ourselves unless we push off of something else to make ourselves move, right? And visualizing and seeing electric fields is like, it's almost like pushing yourself. It's like trying to see the way you see, because this is how we see things. We actually observe, even though we don't even know what electric fields are until we take a physics class, probably. Our eyeballs are designed to notice fluctuations in these things. They can tell when this vector just gets a little bit shorter and when it gets a little bit longer. Isn't that amazing? You don't even need to know what these things are, and your eyes can do that. Your ears do the same thing with pressure fluctuations, right? You don't need to know what pressure is to understand or to hear things, right? Your ears just do it for you. They just do it for you.
It's crazy how like we can discriminate between like such little differences.
Right. Exactly. These little tiny fluctuations, and that's where all of our information comes from. Whether it be seeing something, touching something, tasting something, hearing something, we detect very tiny variations. When we smell things, you guys know what we smell when we smell things?
Like the molecules are hitting
like,
our olfactory.
Yeah, little tiny molecules are literally evaporating off of objects, and that's what causes the smell. Okay.
When you smell shit.
What?
So yeah, it's like it's actually like inside you.
Yeah, exactly. It can get really gross if you think about things that smell bad.
Like vomit.
I wasn't gonna say anything, but.
And
Never thought about it that way before until now.
Yes. So I'm gonna stop right here, and I'm gonna go on Mastering Physics and fix the due date so that you have another week to do this, since we still need to talk about LC circuits and RL circuits. But we're really doing fine on time, because it won't take long to do that. And then we'll talk about AC circuits next week as well, and then we'll get into talking about radiation the week after that. So we're doing just fine on time. I believe we should be completely finished with all of the content of the course in this week right here. So that would be 2 weeks from now. We should be done with all the content, which means we'll have 1 week plus another week. This last week is exams, but this last week here we'll just leave open for extra stuff. And so what that's going to be is, so the way it's going to go is next week is going to be AC circuits, as well as finishing up this chapter. Week after that is electromagnetic radiation. The final week, what we're going to do is we're going to derive Maxwell's equations in differential form, which is the form that you may have seen on t-shirts that have like divergences and curls and stuff in it. So we're going to do that. We're also going to talk about the connection between electricity, magnetism, and relativity. And this will hopefully help to lead you into 1D if you haven't already taken it, because one of the things that okay, I don't know 100% if this is true or not, but my interpretation of what I have read from Einstein, like of his works, is that one of the biggest things that drove him to develop the special theory of relativity was the fact that he realized when he was really young that there was an inherent problem with electricity and magnetism that you can see if you imagine that you're moving along a wire. Because what you can do is you can prove that two different observers would observe different things. One observer would see an electric field, but another observer would see a magnetic field. So that's one of the other things we're going to talk about in this last week. We're going to go through a derivation from the lab manual to kind of prove that it's okay. It's okay if one observer sees an electric field and one sees a magnetic field, because that's how it's supposed to work. And that little piece of information is kind of part of what led Einstein to develop the special theory of relativity. Only one part of it. There's other things that led him to develop it, but okay. So I guess I will see you all next week. I'm going to stick around after class, of course, talk to people about any questions they have about things, but that's all for today.